All right, next up is Doug from Millennium Space Systems. Millennium is a silver sponsor, and they're also in the booth room. With that, I'll hand it off to Doug.
All right, thank you. All right, so as Ben said, my name is Doug Geiger. I work for Millennium Space Systems. I used to work for the Naval Research Lab. Some of you have seen me at previous years when I worked there. So today I'm going to talk about GNU Radio, and specifically about VOLK on ARMv8, and we'll just dive straight in. So I'm going to have a very brief introduction to VOLK. Nathan, I think, talked about it yesterday, and I know tomorrow he has an update. If you're really interested in VOLK, Nathan can talk a little bit better about it than I can, but I want to at least give a little bit of background, and then we'll start diving into ARM-specific things for those of you interested in embedded devices, especially some of the newer ones coming on the market. This may be interesting to you. We'll walk through a little bit of how to do a very simple protokernel in the newest ARM instruction set. I have some initial results to present, and then the conclusion will mostly be talking about where things can go in the future. So, very brief introduction to VOLK. VOLK is the vector-optimized library of kernels. If you're not familiar with it, this was a library that was introduced to GNU Radio a number of years back to enable the use of both SIMD instruction sets as well as other acceleration concepts like instruction level parallelism, some of the other things that Dr. Clancy talked about at the keynote. There was a fantastic talk at GRCon back in 2011, and I like to steal the quotes from that because I think they're fantastic. VOLK is basically the epitome of all problems in computer science can be solved with another layer of indirection, except, of course, the problem of too many layers of indirection. When it comes down to it, VOLK is really just an API and a build system. It also happens to have a library of kernels inside. But really, the idea of VOLK is that you can easily pull in acceleration kernels that other people have written. And I think one of the best examples of that is the Spiral Viterbi decoder that was emitted, the Spiral group at Carnegie Mellon had written. Was actually a genetic algorithm, I believe, that developed that. And VOLK can basically grab onto it, pull it in, and it's now part of GRFEC. ORC, the optimizing runtime compiler, is another example where we can go and basically reuse somebody else's existing code base for doing SIMD acceleration and just wrap it up and make it available to GNU Radio. And of course, for crazy people like me, you can always go in and hand code things in assembly if you really want to. So very briefly, talking about the architecture of VOLK. VOLK is basically provides a description of machines. And so over on the left side there, we have just notional machine one. And machine one is made up of a number of architectures. And these are basically just XML description files talking about what is a machine and what are architectures or multiple architectures might be present. And then there is a collection of protokernels that are available for each of those architectures. Some architectures may not have all of the same protokernels that everybody else has, but based on what somebody has brought into VOLK, there may be multiple protokernels available. And so then when somebody has to write the generic up front. And so the generic kernel is the sort of the front end that says, okay, this is how this signal processing kernel is supposed to behave. We're doing a vector multiply of a 32-bit floating complex value with a sum constant. And we're just going to apply that across the whole vector and then store the result somewhere. And then at runtime, the VOLK dispatcher can actually go and say, well, today I happen to be running on a SSE v4 processor, so I should go pick one of those protokernels. Or even better, somebody has actually profiled this machine and discovered which one of my protokernels run fastest on this particular machine, and therefore that's the one I'm going to pick. Failing that, it always can fall back to the generic kernel, so if your architecture doesn't have any wonderful protokernels for it yet, you always have the generic as a fallback. All right, so the good stuff. ARMv8. This is the latest instruction set from ARM. Any of you not familiar with ARM, it's in all of your smartphones, I guarantee it. The ARMv8 is, I'll say, a very major update to the ARM instruction set. And one of the things that it does is it basically adds this new mode in which they enable 64-bit processing alongside backward compatibility with all of the 32-bit support for all of the code that currently exists for ARM processors. And so they refer to that as ARch64. And one of the things I want to emphasize here is that ARch64 is the 64-bit mode, but if you're in backward compatible mode, ARch32, you do not have access to all of the 64-bit wonderful things that are present in the new instruction set. The other interesting thing about it, and I think this is actually a nice thing that everybody automatically gets to take advantage of, if you are an ARMv8 processor, it is mandated that you have the vector floating point unit and the Neon, the advanced SIMD instruction set installed. This was previously optional in ARMv7. It was usually only present if you had a Cortex-A class processor, so the higher end processors that were in the more power-hungry ARM implementations. And so we automatically have that always on, essentially. It's always there. You don't have to check to see if your processor included vector floating point support when we go and start up VOLK. Some of the processors that it's shown up in, it's been in Apple phones for a little while now. People may or may not be aware of this. The latest Raspberry Pi 3, Model B, is actually an ARMv8 processor. I do want to clarify that all of the default images for the Raspberry Pi 3 are in ARch32 mode, something I'm going to talk a little bit about later, but basically it's there, but it's not enabled by default. In other words, there's some work you have to go through if you want to run 64-bit processing on your Raspberry Pi 3. So a little bit about the differences. What is ARch64? What do we get? It is a superset of ARMv7. So basically everything that was there before is still there, but now there's more. And so if you're in ARch32 mode, if you're doing hand-coded assembly, basically everything's the same. There are some changes required if you're in ARch64 mode to actually detect the presence of the floating point unit or Neon. And that's something that I'll discuss a little bit later. But basically, all of the things that were there in ARMv7 are present in ARch32. They are also there in ARch64, but they call them different things. They changed all of the mnemonics. It's not perfectly clear to me why they did that, but they decided they wanted to name them differently, so they did. ARch64 is basically an opportunity for ARM to make a breaking change to the API, so they did. And so I do want to emphasize, this is a separate instruction set. It's not the same as ARMv7. And so if you're in ARch64 mode, those binaries will not run on older ARM processors. If you care about binary compatibility, this is an important thing. If you don't care about binary compatibility, then you can ignore this. So ARMv7 ARch32 had a bunch of general purpose processors. They were 32-bit wide. And we basically have more now. We have 31 general purpose processors, and they can be 64-bit wide, or you can address them as 32-bit wide if you want to. Neon now has more registers as well. We've gone up to 32 registers that are all 128-bit wide. There were only 16 before. And we can now do double precision floating point on the Neon unit. That's, I think, a huge win for people that care about double precision, which GNU Radio may or may not care about. Yeah, go ahead.
Is it the full IEEE spec now, or because I think the old one didn't have?
So yeah, when do I talk about that? So they have improved the IEEE 754 compliance, specifically for things like denormalization, and I think the not a number spec now, I think they are in full compliance or nearly full compliance for all of those things. So they changed the assembly mnemonics for people doing stuff in hand-coded assembly, which may or may not be anybody else in this room. This is a pretty minor change, I think, in the scheme of things. One thing that's interesting is that the iPhone assembler actually doesn't do things exactly the same as the regular GCC assembler does. And so in ARch64 mode with GCC, you're actually giving the size associated with the operand rather than the instruction, versus in the old style, the size was for the instruction, and therefore all of the operands had to be the same size, for most of the instructions at least. And they basically, instead of calling things like VAdd for vector add, they're now calling it FAdd. This is a pretty minor change. Somebody could probably write a Python script to do a bunch of search and replaces for all of these things and just magically have them work. But I'll leave that as an exercise to the reader. So a little bit more about SIMD and Neon in particular. If you're not terribly familiar with Neon instruction set, they had these 128-bit wide registers that could be presented as different sized registers if you wanted to operate on, for example, 8-bit words or 16-bit or the full 32-bit floats all in a single register. That capability still exists. Some of the naming has been tweaked slightly. They have decided to, they now have this new V name, so V0 through V32. They also can still be represented by Q0 through Q32. Again, why they decided to add this new nomenclature isn't clear to me, but it's there if you want it. So I don't know if Nathan went through a simple example of VOLK. So this is, I think, the simplest example of writing a protokernel for VOLK. This is the 32F x2 add 32F. And for those not familiar with the VOLK naming scheme, basically the 32F x2 at the front means we are feeding in two 32-bit floats as our inputs to this particular single processing kernel. The instruction we're doing is an add, and our output is that 32F on the right. And then we call this VOLK 32. Do I have a laser pointer? We call this VOLK 32F x2 add 32F generic, indicating that this is in fact the generic kernel. This is the reference kernel for how to do 32-bit float adds. And so all we have is an output pointer for our results, and then we have two input pointers. And then we have to tell it the number of points in our vector. So how many times should it go and add things together? And so we have basically we grab our pointers here. We start at 0, and we go in and add A to B and increment through those pointers and store them in C. And that's it. That's how we do a 32-bit float x2 add. So in ARMv8 we have a Intrinsics-based protokernel to tell the compiler to please go use the Neon instruction set to do this add. And so we have this 32F x2 add 32F underscore Neon. That means this is the Neon protokernel. And so the VOLK dispatcher, if we're running on a processor that has a Neon coprocessor available, we'll go in and run this, assuming the VOLK profile hasn't told it to run something else instead. And so we have the same input parameters to this function. We have a pointer for where our output should go, a pointer for our A and B vectors, and the number of points that it needs to operate over. And so GCC Intrinsics basically allow us to tell the compiler, we want you to emit these assembly instructions. In other words, don't try and decide how to do this add for us. We're going to tell you instead, we want you to use this vload Neon instruction and then this vadd to actually go and do the addition for us. And this vadd, because we have 128-bit wide registers, we can do 4 adds at a time. And so we add the first 4 of our A values and the first 4 of our B values, and we store it in C value, and then we need to call vstore to bring it back out of the Neon registers and back into the general purpose registers where it's accessible by the calling program. And so what you can see here, one of the things that is a little tricky here is the first thing we do is we calculate the number of quarter points. Because this particular implementation is going to do 4 at a time, we are now doing number of points divided by 4 in this first loop. That means if the number of points that we were fed in is not divisible by 4, we need to have a little cleanup loop at the end where we go in and say, okay, well, number of points we had quarter points times 4. We now need to finish up any remaining items and just do the standard generic A pointer plus B pointer stored in C pointer, please. And that is our simple intrinsics example of how to do add on a Neon processor. Any questions on any of that? When Nathan and I first did work with the ARMv8 port of VOLK, we found that intrinsics were not giving us a very large speed up on some of the processors we were benchmarking things on, and we couldn't understand why. We had basically taken all of the intrinsics-based kernels that were written for SSE for Intel processors, brought them over to the Neon instruction set, just swapped out the Neon or swapped in the Neon intrinsics for the old SSE intrinsics. Should just work, right? Well, it worked, but it wasn't a significant speed up. And we thought that we should be getting more. And so when we looked at the emitted assembly from GCC, we were kind of disappointed with some of the assembly instructions that it was emitting. We said, you know, we can go in and do better. And so we said, all right, well, we'll just do this in hand-coded assembly, because who doesn't love doing hand-coded assembly, right? So for Neon 64, which is what I have termed the Neon mode in ARch64 for no particular reason, we have this .s file in which we now have our first loop in which we are doing our fadd across our two input V0 and V1, storing into V2, and then bringing it back to a general purpose register to get the results back out. And then we again have our cleanup loop here in which we are doing just a simple fadd over the remaining number of points. One thing I found, and I'll talk about results a little bit later, is that going in and doing hand-coded assembly on ARch64 hasn't been giving me as much of a speed up as it did when we first started the work on ARMv8. And one of my conclusions there is that actually the compilers have improved, and we don't need to do hand-coded assembly nearly as much, which is good news, I think, for everybody. So when I didn't get, my nice, wonderful speed up of doing hand-coded assembly, I said, well, we have a whole bunch of, we have 32 of these Neon registers. We can unroll some of the loops here. In other words, rather than doing a single fadd, doing 4 at a time, and taking my one of my Neon registers, adding it to another Neon register, storing in a third Neon register, I have 32 of these. Let's use some more of them. So rather than doing quarter points where I'm dividing by 4, I'm now doing 16th points, because I can do, how many loads am I doing here? 1, 2, 3, 4. And then I am skipping a couple in here because of the ABI here requires me to preserve some registers, and rather than preserving them after modifying them, I just decided to skip them. And we are basically jumping up to 17 and 18 up here. I seem to have missed 5. I forget why I missed 5. But basically here we now have a number of fadds just sequentially going through the input vector, do them a whole bunch of fadds at once, and now store all my results at once, and then I do still need my cleanup loop at the end. Because obviously if it was possible for things not to be divisible by 4 before, they're probably not evenly divisible by 16 either. So after that little bit of a fire hose about doing assembly, I do want to give some good news. This probably isn't necessary. All of the stuff that we did on ARM intrinsics can actually just immediately be brought over. The GCC compiler understands the old intrinsics mnemonics and automatically translates them to the new ARch64 assembly mnemonics. So unless you know you have to, stick with intrinsics. I'll show that some of the initial results on improvements here in a second. One thing I will note, though, is that in ARch64, we do have to do some changes to VOLK in order to detect the fact that Neon is in fact present. VOLK tries to go and say, hey, is there a Neon coprocessor present? That detection capability isn't actually there because in ARch64, the Neon core is always present, so it's implied. You just, if you're in ARch64 mode, it's there. It's always there. So some initial results. And I'll note that I'm stealing a lot of the work that Nathan did on making nice, pretty graphs, so thanks, Nathan. So running on a Cortex A53 at 1.5 gigahertz. This is, I'll say, a relatively high-end ARM processor that's available on the market now. The Raspberry Pi, I think, runs a little bit slower, but some of the other processors out there run even faster now. So doing a 32 FC-X2 dot product. So this is a complex dot product with complex taps. So this is a FIR filter with complex taps, essentially. One of the interesting things I found here is, so the generic is always normalized to 1 here. So that's the blue line here. We actually end up being a little bit slower with the intrinsics-based one. And interestingly, even with the fused multiply add instruction, we're not seeing any significant gains here. In other words, the compiler is doing its job in this particular case. So at least for the case of a FIR filter with complex taps, we can't do much better than the compiler already can. That said, when it comes to the square root instruction, where we have a 32F taking the square root of it and storing the result back as 32F, the generic is exceedingly slow. And I assume that it's simply not emitting there is a Neon instruction for it is the inverse, or the reciprocal square root, and then we have to take the reciprocal of that, essentially. And it ends up being an estimated square root. And if we simply use the Neon intrinsics version of that, we get a huge speed up. And so, more interestingly, in ARMv8, they added the ability to do the square root straight away in a single instruction. That ends up being slower, and I assume that that's because under the hood, they're actually doing the same thing that we were doing here and just hiding it in a single instruction. I don't know why it's slower. It may just be this particular implementation. On other ARM processors, it may, in fact, end up being faster. It's about comparable to the old Neon one, so it's also available. Similarly, the magnitude function, which also has to do with square root, we get a huge speed up simply by going to the Neon intrinsics version. We also don't get any speed up by using the straight up square root instruction. And I think I show one example here where I am getting a speed up by going to Neon assembly. So this is the unrolled looped version of that assembly 32X2 add function I was demonstrating. And by unrolling the loops, I am now beating the intrinsics-based version. And that's essentially what was required to get a little bit more performance out of my adder for all of the people doing lots of adding. So a couple conclusions here, and really I think what I want to do is talk about where I think this can go. This is a major change in the ARM ecosystem. This is a brand new ISA. They were going in and intentionally breaking things clearly. It is also, they still provided the ability to go to be backward compatible. They still support ARch32, which is everything that was available on ARMv7 is still available on ARch32. But if you want to take advantage of the 64-bit processing that is available now, you need to go and start actually using ARch64. And that requires at least a little bit of work. Fortunately, we can use intrinsics in both ARMv7 and ARMv8, and the compiler just does the right thing. GCC, I'll note, has at least a couple of notes where things may or may not be exactly right. As far as I can tell, anything to do with GNU radio and signal processing, we don't care. And if you really want to go and take some of the old assembly.s files and move them over to ARch64, that's probably just a Python script away, and maybe something that could be done at the Hackfest. So I think I ran a little bit fast there. So I have lots of time for questions.
Yeah, we have a few minutes for questions. Tom?
Thank you. Can you go back to the results? So I'm really curious about some of these results, especially that complex dot product. That doesn't really make much sense. Have we looked at what the generic assembly code gets spit out from the compiler?
I personally haven't, or at least not recently.
Be curious to see what kind of tricks they might be
I
pulling.
think when we did the first ARMv7 work, we took a look at what it emitted. But I did not revisit it here recently.
And then as far as the that square root one with the ARMv8 not performing quite as well, do we suspect that maybe there's our little Intel trick of microcoding before we implement it?
That's exactly what I suspect.
Yeah.
That they are basically, they see, oh, you want to do a square root? Well, under the hood, we're going to do the reciprocal square root and then take the reciprocal for you. And so there's some overhead, I assume, in the instruction decoding that they have to do there.
But we think it's actually they are hard coding their SIMD stuff, like they're doing it properly.
And so this may in fact change in
Yeah.
another implementation of ARMv8. This was obviously in our Cortex A53.
Yeah.
On the A57, for example,
Yeah.
this can be completely different.
Okay, thanks.
So have you looked at instruction timings? So in ARMv7, you have the option of using the dual or quad word registers, and the quad word registers are really just taking twice as long as the dual word registers. Is that still true?
I did not look at the timing for either of the loads of the store, so I don't know if that still holds true.
I was just curious if you've looked at using the inline keyword to have all the stuff appear inline rather than have all the overhead of calling the functions. I found that to be useful.
So VOLK originally, I think, had some use of the inline keyword. My sense is that that either the compiler was already inlining things when it could, or you weren't necessarily saving a lot. So as far as VOLK overall, I think, I'm not sure if if inline is even used anymore, or at least if it's used as extensively as it was. I was not adding inline to any of my work here. These are either separate .s files, which can't be inlined, or the Intrinsics ones, which may or may not be inlined by the compiler.
It doesn't help you if you're in another module. This is the problem.
Yeah.
Raj?
Yep. So Intel provides some tools when you're using the x86 that actually gives you raw theoretical performance of a set of operations, and then it'll actually tell you what percentage of the raw theoretical performance that your assembly is achieving. So let's say you wanted to do the add. They'll actually tell you, using their proprietary stuff that you pay a lot of money for, that you could speed up your add by reorganizing. You're not keeping the pipelines fed or whatever, so reorganizing this way, and you will get 10% more performance. Does ARM itself or any of the manufacturers, or does anybody provide a tool like that actually lets you look at your assembly and analyze it for how it runs on the hardware?
So most of the profiling tools I'm familiar with on ARM are based on perf or the older O-profile. As far as things like pipelinings, I think there is some ability to have insight into, for example, like looking at whether or not the cache is being fully utilized or not. But I don't know of any tool like what you're describing.
Yeah, that's also super expensive. There's also, yeah, that's true. There's also a French dude that has a website where you can like copy and paste your assembly, and it will highlight if you're doing something wrong as like you should unroll here. It worked really well for the Cortex A8, for the A9. It gave some false positives, but I can look around.
Yeah, what is the name of that tool?
I don't know. It's some French dude. I have to Google for it again, but.
Any other questions? Can we get Philip all the way in the back?
Which compiler versions did you use?
So this was all done using an open embedded generated root file system. I think it was GCC 4.9.
Okay, so that could change wildly
Oh, I assume that similar to when we first were looking at ARMv7 stuff, where the compiler version drastically changed performance, at least on the generic and some of the intrinsic-based kernels, I assume that would also hold true for.
Yeah, I mean, basically my conclusion from talking to some guys is the delta between what ARM is doing and getting it into GCC is getting pretty quick now. So I would expect to see better numbers off the more recent builds.
That very well may be true. Certainly the GCC on ARM has made huge improvements.
Any others? No? All right, let's thank Doug. Okay, we now have a short break. This is a 15-minute break, so run to the restroom, get some coffee, get some water, and at 4:45, we're going to start back up with Ballant.